Hi kids, time for triple integrals. So look at this devastating notation, right? It's not that bad. So looking at the triple integral can be a number of scenarios, right? I have two ways here where I've got our dv kind of collapsed and here's our dv expanded. I've given the best case scenario here where our limits are all constants. When we were in double integrals, this letter down here was either R for rectangular region or D for the domain, right? And then the integrand was the function that took the domain up into Z space, right? So think about, and again, different books call this, sometimes they say a G, sometimes, I don't know. There's a lot of conventions that go with this. Doesn't really matter as long as you know this means the bounded region, right? We're never going to be doing these over unbounded, right? So we have some region that we can kind of keep in a box, if you will. Think of B for box. As long as you match your limits of integration correctly, you can put this, because your limits are constants, you can put this in any order that you like, right? Just match it up correctly. And further, if your integrand is like a product of X, Y, and Z, you could literally make 3 integrals, right? 3 integrals and multiply them together and you'll get the same result. But what's going on, right? It was challenging enough to think about this in 2 space where you're like, okay, I have a point down here in a domain region. It's an X and a Y. I kind of put a rectangle around it, map that up here into, my space. And I'm taking this area, multiplying it times the height, and I get it. That's volume. And then I'm going to sum them all up, and I'm going to get the volume of the whole solid there. I get it. Volume. Yay. But what's going on now is that the region down here, I want you to think of itself having thickness or height. So when I pick a point in here, it's now got an X, Y, and Z coordinate. So that blob is like 3 dimensions. And so the function has to now be in terms of X, Y, and Z, right? And I no longer can just draw a rectangle around this. I have to draw a box around it. Right? And then I'm multiplying all those volumes and adding some, what's going on? There's actually a name for this. What you get when you are taking all of these cubes, having all these volumes and multiplying, it's called hypervolume. Kind of cool name, right? Makes me think of a hyperdrive in Star Wars. Hypervolume, what the heck? What is that? So there are multiple applications of hypervolume, in college level physics and engineering and chemistry, biology, that kind of thing. I think the easiest thing for me to try to conceptualize what's going on is referring back to what we did in single variable calculus when I did things like, hey, when we first learned about integration, right? I was like, what if these units were seconds and the units on the vertical were feet per second, and an integral is a product of your heights times your infinitely small widths. And oh my gosh, I get feet or distance out of that as long as I'm always above the x-axis. Right? So we started off with that. Well, what if I told you also, what if I just put meters on both axes? That doesn't change the fact that you're multiplying meters times meters, right? Height times width, and you get meters squared, which is area. No big deal. Well, what about if I put area on the vertical axis? Okay, so my product is meters squared times meters, which is volume. Well, what if I put volume here and on the vertical axis I put density? Density is measured in kilograms per cubic meter, right, or mass per volume. When you integrate, you are still doing a product, and you get kilograms out of that. You get mass by integrating. So as long as you have your integrand, right? If your integrand is in the units such that they will cancel out with your horizontal, if you will, units, right? In this case, integrating density dV gives you mass. Let's look at another picture. So look at this one. This is, okay, I'm in like geometry, right? In middle school geometry. Find the volume of this rectangular solid. 3 by 4 by 5, right? No big deal. Woohoo! But can you see that's what this is doing, right? I'm kind of like going from one, kind of like building integrals, if you will. Notice the integrand is just a 1. So I'm integrating from 0 to 5 delta z. That's a linear issue, right? Think about what you would get from that. Then you're going to take that and integrate dy. Well, that's going to give me area, isn't it? Then you're going to take your area and multiply dx. That's going to get you volume. And you know what? If you did this each time with your integrand of 1, you would end up with 60 when you're done. But there's an assumption that you haven't really considered, or maybe you have. Oh, I forgot. I have this, I literally have this picture. This is like a 30-second video where that picture is, you can see it being cut up into all these individual like little ice cubes. Right? And so the idea of having the volume of each one of these, finding the volume and adding up all those volumes of each little cube, right? The assumption that we're making is that the density of each little cube is constant. What if it's not? What if it's not? What if the density maybe at corner here is nothing, but the density up, down there, right in the middle of this thing floating inside it's very dense, whatever this material is made out of, right? However this is constructed or made. So look at this. Your integrand is not a constant. I don't particularly like when they write out the box dimensions like this, but nobody really cares whether I like it or not. So hopefully you can see from there how I set up my limits. And I made sure to match. If I put X on the inside, Y in the middle, Z on the outside, I matched up the numbers correctly. So if I tell you that my density function is my integrand in kilograms per cubic meter, dV is in volume, I'm going to break dV up into dx, dy, and dz. My integrand is just a product of x, y, and z, so this is a simple one to break up. Right, and each one of these is not a challenging integrand. Each I'm going to have a half and the variable squared. So what is this? This is going to be just a half because I have a 0. This is going to be 4 over 2 minus 1 over 2. And this is going to be 9 over 2 minus 5 over 2. So what do I have here? 8 times a half times 3 halves times, oops, sorry, that's a 4, 5 halves. So 2 times 2 times 2 is 8, all in the denominator. So I end up with 15 what? 15 kilograms. Now, most of the problems that you're going to be doing and practicing don't have units attached to them, but I like to do this with units at first. So when you get that 15, you kind of have a concept of what it might mean. If those units are attached, you found, right, 15 kilograms is the mass of this box, if you will, where the density varies. And hey, if we are talking mass and density, you know what else is coming, right? What do you think the center of mass formula then looks like? Well, hello, you just did it, right? It's just your density function is x, y, and z dv. So what is x bar, y bar, and z bar going to be? Same triple integral, same limits, same row. But the x bar is going to have an extra x, y bar is going to have, whoops, sorry, x bar is going to have an extra x, y bar is going to have an extra y, z bar is going to have an extra z. Oh, I forgot my dv on that last one, didn't I? Now you better hope I don't ask you to do one of those, right? I just ask you to set it up. Notice that before I started talking about center of mass, these directions did ask me to evaluate, and I ended up with 15. I was given units, so I'll give them units back. With many of these problems, I'm just going to be asking you to set up. So make sure to read the directions. Now, what if the region that we're talking about isn't a box? And I'm not talking about this here. I'm talking about your limits, right? When, if you looked at the previous problem, you had x, y, and z's, right, were all constants. You don't have a nice little prism, or rectangular prism. You've got a blob, right? So that means you have some equations for your bounds. Whereas if you have a box with x, y, and z all constants for your limits, right, you have all straight edges. So what if that's not so? It's going to be really important, even as poor a job as you may do, and you can't do any worse than me, that you try to make a 3D sketch so that you can determine the equations of the bounds. And this is your innermost integral. Then from there, and you've got 3 scenarios. We're going to talk about each one. After your 3D sketch, you want to make a 2D sketch of your blob, which is really a projection. And you need to think about which plane your projection is in, which helps you with the outer 2 integrals. Then you're going to evaluate the inside integral, and then you've just got your double integral left. Right? Now, this is why I want you to set up most of the time, is because you've been doing a bunch of integration. I've seen you do a bunch of double integrals, so I don't really need to see this piece. So when you look at your homework, I gave you a lot of homework problems But there's only 4 that I want you to do all the way through the integration. The rest of them, just practice setting up. So here are our scenarios. If I have my blob down here, if my curvy bounds are z equations, you have a top and a bottom. Top minus bottom is going to be your limits here. Your projection, if you're looking down the z, your projection is on the xy plane. Now, your book or website, I can't remember where, I've loved to refer to this, or gazebo problems, and they call this space G, and they put the G under here. I just really can't get into that analogy. So if you like the gazebo analogy, please use it. For me, I'm not really going to be referring to the gazebo. So notice this situation where this time, where are my curves? My curves are x equations. X equations, and I have the front and the back. That's what's going to go here. The equations that determine your front surface and your back surface. When you're looking down the x for your projection, your projection is in which plane? The YZ plane. Lastly, look at your curves. Right and left. Your equations are y equations. Look down the y-axis and project onto which plane? Okay, so those are the 3 scenarios that you're going to run across when you don't have your box, right? Where all your, whereas before, right, you had this kind of scenario, right? It's a terrible box. I know. Let's try an example. So things to note about the directions. Set up. You're not asked to integrate. No integration if they're just asking me to set up. They're asking me to use a triple integral to find volume, self. If the triple integral gives me regular volume, my integrand is a constant. If it's not 1, suck the constant to the outside and make the integrand 1. So what do I have here? Now, I do have a picture of this, but I'm going to show you that you can figure out what you're doing even if you're as bad of an artist as I am. So the first thing I notice here is that I'm giving a plane z equals 1. I have another plane. That one was in terms of z. I think I'll get this one in terms of z. Right? So I can kind of something like that. Then I have a cylinder where Z is free. So this cylinder, oh, I'm going to draw it up here, right? Because I was supposed to stop at Z equals 1. Right now, that's not a great picture by any stretch of the imagination. But I hope that you can see from here, I can kind of think of, well, I have a bottom. What's the top? Now it's like, again, my picture's terrible, but can you see that if I'm enclosed, that the top is going to be this plane? I have a Z and a Z. Z equals 1 certainly lies below Z equals 5 minus X. Then I look down the Z axis and project onto the XY plane. And I make a 2D drawing of that. In the XY plane, and now I think about my integral. Since I had the top minus bottom, and they were Z equations, I'm going to do this. Check my 3D. Now go to your 2D. What strips should I draw through 2D? Should I draw vertical strips or should I draw horizontal strips? And I think you can see that vertical strips would be pretty good, which means right? And if you think about the boundary here, this boundary is the top of the semicircle. The boundary of this strip as I move through the region between -3 and 3 is the bottom half of the semicircle. And then my last one should always be constants, right? This strip goes from -3 to 3. And I don't have to integrate. They didn't ask me to. They just said set up. Now, again, I do have, that was all with that horrible, horrible, horrible picture. I have a better one. And you can see me trying to draw the plane, how it kind of squished that side of the cylinder. Here's my bottom and top. Here's my projection into the XY plane. Here's the strip I drew. And as I swept through the two-dimensional space, that helped me decide what I was putting here. These were Z equations, so I integrated inside dz. I had a vertical strip, so I had to have Y equations here. And here were X constants. Remember, your outside is always constants. And my integram was 1. So I am just integrating and getting cubic units out of this, volume. Let's do another one. Again, read the directions. Set up, but notice your integrand is not a constant. And then want me to set up this picture. So I'm bounded by x equals 0, y equals 0, z equals 0. And then I have an equation here. What does this look like? Just draw intercepts, right? When x and y are 0, z is 1. When x and z are 0, y is 1. And when y and z is 0, x is 1. There's my 3D picture. Can you see that there's my top? What equation does that come from? The top of that solid tetrahedron. Right? So who's your bottom? Who's the bottom then? So I have z equals top, bottom. Let's go to our 2D sketch. Looking down the z-axis, I'm going to be on the xy plane. And what do you see down there? What do you see projected down there? Right, I still have intercepts of 1 and 1. I have that triangle. What kind of strips can I draw through that triangle? Well, it doesn't really matter, does it? Right, your bounds don't change no matter whether you draw horizontal or vertical. I'd usually tend to do vertical is my default. Oh, I forgot to put my DZ here. So if I do vertical strips, then I have to have Y's in here. Y equals 0. And then the top of these strips are bound by what? And then X is left, right? And these strips are going from X equals 0 to 1. Okay. Now they did just ask me to set up. If you want to try this one actually isn't too bad. I get 1/24 when I'm all done. You can do that on your own and see if you get something similar. Forgot that I wrote those. Another example. This time, they want me to evaluate. My integrand is not a constant. And look at my region though. Look at these. This is giving me a hint of what I'm dealing with. Right? So unless something makes me change my mind, right, I think I'm going to be starting with Y values. So let's make a 3D sketch. What is this? X squared plus y to the first is equal to x squared plus z squared. You know what that is? right? That's a paraboloid. And what's this? Y equals 4? Right? There's a plane there stopping the paraboloid. Right? So I'm finding the volume of that. There's my 3D sketch. Look down the y-axis for your 2D sketch, and you're going to be on what plane? Right? You're going to be on the XZ plane, right? I mean, again, it's a terrible drawing, but it's good enough. Good enough. So what am I going to do with my triple integrals here? Firstly, I don't have a top minus bottom, do I? Right to left. Who's my right? And my left is the curve. So my first delta is delta y. Now go to your 2D region. If I draw these strips, right, look at those strips. That means I'm going to be D what next? Z, right? So this again is the top of the circle. What's that equation? That's when x squared plus y squared, right? Set those equal to each other. Bottom of the semicircle, top of the semicircle. And then what do you have left? These strips vary between what? -2 and 2. Right? Now, again, I could have set this up other ways. In this case, right, I could have looked because the curves were pretty simple, but because my y's were already by themselves, if I had wanted to do a top minus bottom, I would have had to have gotten the equations in different forms, right? I don't think it's worth it. The only way it would be worth it is if my integration wasn't going to go well. So I'm going to erase this so that I can, because I did have to actually evaluate. So I'm going to erase this so I can give myself, well, I guess I can start it. So when I integrate here, and again, I can't do my cute little 3 products, right? Not with these kinds of bounds. So what happens when I integrate this red integrand with respect to y? I just get what that red integrand times y, right? Now, I hope something is starting to happen in your brain at this point. Because when I fill that in, again, I'm just working inside this blue thing. When I fill in, I've got x squared. Ooh, I hope did you catch this already? This needs to be turned around, right? The right function is y equals 4, and the left function is the curve. I think I said the right thing, but then I wrote them incorrectly. Times y. Apologize. Y is just 4 minus times another x squared plus y squared. Now I'm seeing an awful lot of, I keep writing y and it's freaking z. I'm seeing an awful lot of x squared plus y squareds, x squared plus z squareds, gosh darn it. I've got circles here. I've got circles here. I've got circles here. I've got x squared plus z squared there. X squared plus z squared there. What is this making you think of? Yep. Polars. Polars is going to make these equations look a little nicer than they are right now. So let's clean this before I ever think about these. Let's clean this up a little bit. So this is going to be, I'm going to factor out an x squared plus z squared to the 1/2. Pen is being so weird as well. So then what am I left with? The 4 minus x squared plus z squared. So for polars, normally, which is why I kept saying x squared plus y squared, right? Normally, r squared is x squared plus y squared, but that's okay, right? So I'm in the xz plane. That's all right. If I say r squared is equal to x squared plus z squared, then what do I have here? This is just r, right? And this is 4 minus r squared. That's a lot nicer looking than what I had over here. Now look at what I'm going to do with my bounds, right? Just like what we did before. What am I going to do with my bounds? What's my radius? My radius is just 2. And my theta is all the way around the circle. So I'm going to end up with 0 to 2 pi. Oops, sorry, I don't need that third integral because I already did the inside. And my radius goes from 0 to 2. And I'm integrating r times 4 minus r squared. But do you remember what you have to do when you're transforming from rectangular to polars? What do you have to do? your extra r. Come on, pen. I'm gonna now I'm gonna erase this because this is getting really messy. Multiplying through, I got 4r minus r cubed. R d theta. I can break this up now. Which is just going to give me 2 pi, right? And this is 4r squared minus r to the 4th over 4. So integrating that, whoops, sorry, this is just r to the 4th. I was already thinking of integrating, wasn't I? So what do I have here? 4 times 8 over 3, right? 2 cubed is 8 times 4, 32 over 3, minus 32 over 5. And then, of course, minus plugging in 0, but that's going to make that go away. And when you do this, you get 128 pi over 15 after you get a common denominator. Whoa, that was a lot. But again, all your homework problems, I only ask you to integrate 4 of them. Practice just setting up the rest. Wow, good job. I'll see you in our live session. Oops.